Hello, my name is Paul Wilson and I'm here with my colleague David Clement. We are the engineers in control. This is the sixth talk in our series, Control Systems 101. In talk number 6, we are going to construct a differential equation for a mechanical system. I'm going to use the classic motor vehicle suspension system problem, the mass spring damper system. Only in Australia we don't call dampers, we call them shock absorbers or shocks. Remember that to create a differential equation we need a balance equation. And here the balancing act is the balancing of forces according to Newton's law that every force has an equal and opposite force. So let's start with the first component. Here we have the inertia reactive component, which is kinetic energy. It comes from the mass of the vehicle, and mass does not like change. Mass likes to resist a change in velocity. When you try and accelerate mass, it kicks back and you need to use more force. So here's the equation. So we've got m for the mass of the vehicle, Fm is the force on the mass, and x is the distance. And force is mass times acceleration. So the equation here is Fm equals m, the mass, multiplied by the second derivative of distance, in other words, the acceleration, d2x by dt squared. Now let us have a look at friction. Friction is a passive energy loss. All it does is turn energy into heat, and the heat is lost to the atmosphere. That's a very simple equation. So we have a friction constant C, we have Fd, which is the damping force, and V is the velocity. And of course velocity is the derivative of x, the distance. So force is friction multiplied by velocity, and so the friction force Fd is C, the friction constant, multiplied by V, the velocity, which equals C multiplied by dx by dt, the derivative of position. And the last of the three, we have the spring. The spring is a reactive component and holds potential energy. As it compresses, the potential energy is positive. As it stretches, the potential energy is negative. Very simple equation. The force is proportional to the distance, the position. So we have K, the spring constant, Fs for the force on the spring, and x for the distance. And the equation is quite simply Fs, the force, is K, the spring constant, multiplied by x, the distance. So now we can bring it all together, and we have three forces to add up. We have the mass times the acceleration. So this one is the mass. And then we have the friction of the shock absorber here. And finally we have the spring. So we've got the addition of all the forces, so mass times the acceleration, d2x by dt squared, plus c, the friction constant, multiplied by the velocity, dx by dt, and the spring multiplied by the position. Now we can add a perturbation in, and so if we hit a bump, the perturbation and all these forces try to settle to a final position at rest. And that gives us the differential equation for the mass spring damper system. It is interesting to note that in the early days of motor vehicle suspensions, they were designed using analog computers. And certainly when I was young, when I was a student, I grew up in England, and the British cars, the suspensions was fairly stiff, and it always amused us that American cars had very soggy, soft suspension, and they were designed like that. Of course, control engineers do not work with differential equations. It's messy, it's difficult. We just don't have the time to waste on differential equations, so we use a different method. And in talk number 7, I shall introduce the method that control engineers use, and that is the variable S and transfer functions. Thank you for listening to talk number 6, and I hope you will join us again for talk number 7. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement. All rights reserved.